Okay, so good morning, everyone, and welcome to the Geo-Lesson webinar series. Geo-Lesson is a platform developed to connect professionals, researchers, and students through educational discussions focused on sustainability, resilience, and emerging engineering challenges. It is our great pleasure to welcome Dr. Nirupam Aich, the Richard L. McNeel Associate Professor in the Department of Civil and Environmental Engineering at the University of Nebraska-Lincoln. Dr. Aich leads the Aich Laboratory for Environment, Nanotechnology, and Sustainability. His interdisciplinary research combines environmental engineering, nanotechnology, material science, advanced water treatment, and artificial intelligence to address emerging contaminants such as PFAS and microplastics. He has published more than 70 peer-reviewed articles, holds multiple patents and invention disclosures, and has secured more than 6 million in research funding. Today, the topic is from contamination to compliance, understanding PFAS risks, regulations, and remediation strategies. Thank you very much, Dr. Aich, for joining us today. The floor is yours.
Okay, thank you, Adrika, and thanks to the Geo-Lesson team for reaching out and asking me to present on this topic. This is, you heard some introduction, obviously, but I will give a little bit more introduction of myself. So I don't know how many of you know about Bangladesh, but I originally am from Bangladesh. Like, I was born in Bangladesh, which is a country that is 66 times smaller than US, and 1.35 times of Nebraska, a little bit more, but has a huge population, like 180 million population. Okay, something is happening. Let me go there. Okay, yeah. So it's half of US, so it's 90 times of Nebraska population. In Nebraska, we have like 2 million population. Different states have different sizes of population. So the reason I talk about this is, like, if you look at the size of Bangladesh versus US versus many other countries like China, Russia, so you can imagine that, like, the population density is very high, and that creates a lot of stress on resources, including water and everything, right? So that's what, like, drove me to go from chemical engineering. So I did my bachelor's in chemical engineering in Bangladesh University of Engineering and Technology, and then I moved to do my master's in environmental engineering and PhD also in environmental engineering in US. And actually, my undergrad thesis was also on water treatment. So that's what kind of inspired me to keep working in environmental issues and water issues. So, and I joined in as an assistant professor at University of Buffalo in State University of New York in 2016. Then I joined UNL as an associate professor in 2023. So you can see, like, I have traveled quite a bit and over the last 16, 17 years. So it's this is my sixth state staying in US. So it's been quite a journey. And if you don't know where Nebraska is, this is where Nebraska is in the map of US, okay? So it's kind of almost in the middle of the country. It's quite a big state, but we are majorly, like, Lincoln is in the southeast corner, near the southeast corner of the state. And the vast majority of the state is basically cornfields. Like, Lincoln is a small, not only, it's not very small college town, it's a 300,000 population. It's the capital of the state. And this is our state capital. This is the university campus. We call it City Campus. In City Campus, we have a new College of Engineering building that was established in 2024. But our civil engineering department and environmental engineering department is established way ahead of time. So I'm like, this is our building, but we are very excited to announce that we are going to celebrate our 150-year anniversary this year of this department. So the school goes a long way back, and we have really good facilities for environmental engineering labs. We have a process lab. We have, like, sort of fume hoods where we do our material processing or other experiments. Then we have instrumentation lab where we have different types of instruments, including analytical instruments like gas chromatography mass spectroscopy or liquid chromatography mass spectroscopy, which are important for analyzing different pollutants in the environment. So I will talk about a little bit overview of our group. We are known as Aich Laboratory for Environment, Nanotechnology, and Sustainability. We have really good group of people, like, and obviously with research teams, they change every year, every other year, a few years. Right now, this summer, we have really excellent undergrad students and high school students who joined our group for the summer research, but I have also 3 PhD students currently working with me. In the back, you can see them, but here are some of the former students listed, like PhD alumni. I have graduated 3 PhDs. I have a postdoc alumni that worked with us for couple of years. And we have had a lot of undergrad researchers, including the ones that you have seen in the other picture, but we have 3 PhD students. The reason I talk about them because they are the main people who are really doing the work that I'm going to talk about. But mostly I'm going to talk about what the problems we are tackling. So kudos to these really excellent students who really do the majority of the work that we do in the lab. Okay, so our lab is actually looking at environmental and water issues mostly. The problem that we try to tackle is polluted water. Trying to understand the problem first. So we have to understand where the problems are. There are chemicals, plastics, and other pollutants in the water. So then, once we understand the problem, we want to understand how we can design new solutions. So we try to solve this problem by designing new materials. So that's where the nanotechnology comes. Okay. So we use different types of experiments. We are primarily an experimental lab, but now we are developing data science-based tools to make predictive design of materials. So the goal, but at the same time, what we try to do is look at the sustainability of newly designed materials too. So it's not like we are designing new materials to solve the problem, but we are also trying to understand if these new materials are not creating an issue for the environment too. So overall, we want to clean our water and like gather useful resources from wastewater for the future. So which is really an interesting thing. So I have given a lot of things about other things about my lab, and but what problems we are focusing on. And I'm not going to talk about a lot of different problems. We are going to focus on PFAS. Many of you probably heard about forever chemicals or PFAS, or I'll go to the exact definition. But if you haven't done haven't gone known about it, I would suggest watching this movie, Dark Waters, if you haven't watched it. It is from 2019. It shows a chemical pollution problem that is caused by PFAS in West Virginia back in early 2000s. Like that was discovered by this lawyer who was actually working for chemical companies, but then he went against, it's not went against the chemical companies, it was more like he was trying to figure out how PFAS or forever chemicals are creating a problem for environment and for people and human health. Okay, so I would suggest you watch this movie to get more like non-scientific or in a different way, get introduced to this chemical and the issues. And I'll give more introduction. So if I talk about it in the right side figure, you can see that there are a lot of different chemical structures, but you can see that these are all aliphatic chains. There are some aromatic chains like carbon fluorine bonds, and I will go in depth here. So you can see there are a lot of different structures. That's what you take from here. And the reason, I'll come back to this reason, is that how we get this structure. So these are PFAS or chemical structures. So in what are these PFAS structures or chemical structures? So par and polyfluoroalkyl substances, this is a very long name. So we call it PFAS in short, like taking the PFAS, right? Alkyl substances. So we are talking about PFAS. So the main thing is that if you think about hydrocarbons, like carbon-fluorine bonds, like methane, ethane, like large-scale chemicals with large chain chemicals like carbon, hydrogen. So if we remove the hydrogen and put fluorine in it, that's when we create fluorinated chemicals. Okay, so back in 1940s, when World War was happening. So DuPont and 3M, these chemical companies came up, synthetically designed these chemicals, which were made of carbon and fluorine. And carbon fluorine bonds don't necessarily exist in nature. Okay, so what happened when they created this molecule, and this is one of the first molecule that was created, this is known as perfluorooctanoic acid. So if you look at it, there are 8 carbons and then carboxylic acid group at the end, but most of the other bonds, all of the other bonds are connected to carbon hands are connected to fluorine. Okay, now carbon is mostly positively charged. On the other hand, fluorine is the most electronegative atom in our periodic table. So what it does, it pulls electrons in a bond towards itself. So it becomes very negatively negative. On the other hand, carbon is positive. So when carbon and fluorine are bonded together, they make one of the strongest bonds possible in synthetic chemistry. Okay, so which was really good for several reasons, because it was one of the strongest bonds, so it can resist heat. So even at 1000 degrees Celsius, you cannot break these bonds. So you can really use it for explosives. So that's why it was created in the first place in 1940s during Manhattan Project to build atom bombs. PFAS was created for that. PFOA was created for explosive and making coatings for explosive and other things. The other thing was that they are highly resistant to water because they have long chain carbon chains, so they are very hydrophobic, but at the same time they are very oleophobic too. So you can create more like resistance to water and oil at the same time, which is really unique, highly hydrophobic, oleophobic. It's really a unique combination of things. So what they did is they took during World War II, they wanted to have the tanks, like that armor tanks or vehicles that were made of steel. They wanted to coat the surfaces of those steel with hydrophobic uh, coating. So that's why they came up with PFAS. And one time, once they created this, they realized that can't we use it for consumer products? So from that there, we got firefighting foam, we got fire extinguishers, we got non-sticky cooking pans, we got Teflon, right? All these things that we use for any waterproofing, any oil proofing we do, we got it from there. Okay, so these are some of the examples. So there can be actually more than 15,000 different type of structures, because you can take these carbon chains, you can make them short, you can make them long, you can put fluorine in different places, but replaced with hydrogens. You can have different types of functional groups there. So you can create a whole range of different sets of chemicals structures with that, and you can get different types of properties and you can tune the properties of it. So it's really, really unique. So if you look at these first two PFOA I talked about, then there is PFOS, which at the end of this structure, carbon structure, you have the sulfonic acid groups instead of carboxylic acid group. Even this small change can create property differences between this. So these are the two chemicals that are already banned from manufacturing, because it has been discovered that they are really linked to cancer. They can cause cancer in humans. And then what the company started to do, that these two were banned, so they started creating these other chemicals, shorter chain chemicals, and understanding that they may not create problems for humans. That was the understanding. But eventually we figured out that there has been a lot of studies that is going on toxicity and understanding of how PFAS replacements or PFAS short chain PFAS cause toxicity and bioaccumulation. They are also being a problem. Why they are a problem, right? First of all, if you look at the product side, so if you think about non-sticky cooking pans to food products, right, food packaging, right? Think about the Starbucks cups that we think about. So we think that Starbucks cups are good because they are paper made, right? But how do a paper get not? How do a paper don't get wet with water in it, right? Because we are creating a water-resistant layer on the surface, and we are using PFAS for that. So if you think plastic is bad and paper is good, probably not the case. Actually, paper making industries use probably one of the highest amount of PFAS in the world. Okay, so it's really crazy to think about it, but this is the true nature. So what happens when we use them over time, they can get released in our environment from manufacturing of these products or usage of these products. They can get into the environment. Now, because these carbon fluorine bonds are really, really strong, so typically what happens with synthetic chemicals, you have microbes in the environment or other organisms that can take them up and break carbon hydrogen bonds in most of the hydrocarbons. But for carbon fluorine bonds, they cannot do it. So they keep persisting. So that's where persistence come. They have a huge half-life, like thousands of years to few hundred to 1,000 years half-life. They don't degrade in the environment. At the same time, they release very small amount in the environment. So when we say emerging contaminants, it's not like PFAS was not in the environment before, but we didn't have the analytical capability to identify them. Okay, so they have been being released from 1940s because we are making from 1940s to now, but we were not detecting because they get into our water in so much smaller quantity. If you think about milligram per liter, that's parts per million. If you think about parts per billion, that's 1,000 times smaller, and microgram per liter. But PFAS exists in nanogram per liter and less or less. And they're very, very small. So it's very difficult to detect them in water. But they can be persistent. But then what happens from all these different products or different things like through water, food, then direct contact, we get them inside our body. Once they go inside our body, now if you think about PFAS structures based on carbon and fluorine, they can be very, very hydrophobic. So when they go inside our body through water too, they don't want to stay in the water. They can get inside our body and start to bind with our organs and tissues because our body is made of carbon. So they really like carbon and they get inside our body and they start building up over time. Okay, so that's the first thing. That's accumulation. Bioaccumulation is happening. Second issue is that when they start building up, they will create problems. They will change the structure of the tissue, the structure of the cell, DNA modification will happen, and that creates cancer. Okay, chronic exposure can lead to cancer. There are a lot of histories, so you can see like a lot of diseases that can happen. Like thyroid cancer is one of the most prevalent one. Issues to reproductive system in both men and women are a major issue that is connected to PFAS. Then you have like developmental disorder in a child, like they can have decreased birth weight, they can have okay, somebody is okay, good, thank you. So you can see that these are a lot of issues like human health issues that are being created because of PFAS. So and there are so many of them, so it becomes an issue. So now, if this is an issue, we have to understand the problem, where the problems are, right? Where we get PFAS from. So in many cases, we are using or making PFAS in urban areas and manufacturing, and then from there, most of the time, this PFAS, we can think about how PFAS moves in different ways, air, water, soil. But first, because I'm more on the water side, let's look at the water and how it goes from there. So we have sewage water, that wastewater or municipal wastewater or industrial wastewater that goes to the wastewater treatment plant, right? So PFAS goes with there too, with other contaminants too. Now, wastewater treatment plant and drinking water treatment plant, they were not designed for taking out PFAS or these chemicals when we designed them. Okay, and we are figuring this out now. Now, what happens in wastewater treatment? There can be two things. One, because they are not being taken out, they can go out with our effluent water to natural reservoirs like lakes or other rivers. And then they can come back to our drinking water treatment plant. And through that, if drinking water treatment plant cannot treat them or remove them from water, they come back to us in tap water. Okay, so that's one way we are getting exposed. The other way it can be exposed to the environment is that in wastewater treatment plant, there are biological sludge, okay, solid sludge that is there. Okay, bacteria, biological wastewater treatment plant creates a lot of solid sludge dead with dead bacteria, and they become biosolids. So what happens, because PFAS is very hydrophobic in many cases, the long chain PFASs, then they can get attached or absorbed. They are not being degraded by microbes, but they are getting attached with the dead cells. Okay, so they are removed in biosolids. So why biosolids is a problem? Because biosolids, in most cases, wastewater biosolids are used as fertilizer because they also contain a lot of nutrients like nitrates, phosphorus, other nutrients. So, for example, in Nebraska, 95% of biosolids are actually used in farmlands and many states too. So now people are figuring out that biosolids can also create a problem for farmlands where PFAS can be eventually leached from that biosolids application, right? In the state of Maine, they have actually banned biosolids application in farmlands because of PFAS related pollution. Okay, so they can go into groundwater, they can come back through private wells. They can go into like cattle grazing, like cattle, beef, or other like goat or sheep. And when they're grazing in the farmland, then they can also get contaminated with PFAS. The other side is like when we take out solid waste, we put them in landfill. From there, if you think about all these Starbucks like food packaging and all these things, like when they go into the landfill and they are being disposed, and over time they can leach PFAS from there. Okay, so landfill is another case where you will have PFAS contamination. A major part of like PFAS contamination are firefighting foams, because if you think about all the fires we have, the wildfires we have a lot of army military bases that use a lot of explosive for training. They have to use firefighting foam all the time. So they also create a lot of problem for these army, military, navy, air force bases. And those defense infrastructure actually has most of the PFAS contamination compared to municipal contamination. Like if you look at the concentrations, you will be amazed like how much more contaminated defense infrastructures are. Okay, so they can get into our water, they can get into our soil, they can also get into our air. I'm not talking too much about the air side too much, but what happens in that case, if you think about, we are getting PFAS in water, we are also getting them in soil, and from soil they can get into our food products too. Okay, so there are studies that have shown PFAS contamination in beef. There are studies that have shown PFAS contamination in milk, and typically organic milk may have more PFAS there than, like non-organic milk. Okay, so these are not conclusive. So, but here is a study that you can read this series. So New York Times came out with like several PFAS articles back in 2024, September of 2024, around that time. So this was one of the first articles that talks about PFAS and forever chemicals. I forgot to mention one thing, why we call them forever chemicals. This is because of carbon-fluorine bond breakage doesn't happen. So they can, like, because if you think about our lifetime versus PFAS's lifetime, if they're existing for 1,000 years, it's already forever, right? So it's kind of like forever chemicals when they can exist for quite a long time compared to human life cycle. Okay, so what this article talks about, this is a case of a Texas ranch where they found a stillborn calf, like baby cow, which was already dead when it was born, and then that tried to figure out why they are having stillborn calves. And they took this baby like carcass of the calf to testing, and they found that there are 600,000 parts per trillion amount of PFAS in the body. Okay, now for people who are not familiar with PFAS contamination or like the scale of the contamination, here is the thing. If you know about nitrate contamination, nitrate drinking water nitrate levels are like safe levels of nitrate in drinking water is 10 milligram per liter, okay, which is 10 ppm, parts per million. Billion to trillion is 1,000 times less, and millions to billions is 1,000 times less, and then trillions in another 1,000 times less, right? So when we look at what EPA suggested for PFAS regulation is the maximum safe level of PFAS contaminant level that was proposed in drinking water for PFOA and PFOS back in 2024 is 4 parts per trillion. So just compare this 4 parts per trillion versus 600,000 parts per trillion. So it's a huge amount. So you have to understand that compared to nitrate and other contaminants, this PFAS level, you need very, very small amount of PFAS for a chronic dose to have issues, okay? If you look at this one, this column, maximum contaminant level goal, what it says, PFOA and PFOS chemical, if these are the two major ones. And if you look at the contaminant level goal is 0. What does that mean? Means we should not have any PFAS in our water, okay? Like at least PFOA and PFOS. So, which is like really, really important to understand. And in April 2024, EPA actually came out with regulations for total 6 PFAS. But this year, because this is a new administration after 2024, so we have a new regulation now where the other PFAS are not being targeted, only this PFOA and PFOS is regulated. Okay, so this is for drinking water. Okay, so what it means from this discussion is that in drinking water, we have very low level of PFAS that we can have. Okay, so that's the main thing. We don't get only affected by PFAS through drinking water. We can get affected by PFAS through food. We can get affected by other ways, right? Direct contact from carpets, from all the things we use. Honestly, anything you see that you want to be waterproof, fireproof, oil-proof, potentially has PFAS, which means everything, almost everything that we use. Okay, so the second part of this is that the reason EPA is regulating drinking water and not food or other things is that that's the only thing you can actually control. Food is about people's behavior, consumer behavior, right? Other ways like you cannot control behavior. So although only 20% of PFAS exposure happens through drinking water, but we can control drinking water regulation. Okay, here is the thing. If you think about, I don't know about bottled water, but whoever drinks bottled water and thinks that bottled water is better than tap water, to break to you, it may not be, because bottled water is not regulated as much as tap drinking water. Okay, so I'm not saying they are bad. I'm just saying for people who don't know it, this is an important information to know. Okay, so coming back to PFAS. Now, how do we solve this? So in 2024, when this regulation came, one of the important thing came is that I said like drinking water treatment plants are not really equipped with taking out PFAS. So what it means that now you have to design new treatment processes or to take out PFAS from water, which will cost about approximately $200 billion to $1 trillion capital cost for water utilities in US. Okay, is there a question? Somebody has a question?
Oh yeah, I had a quick question, like regarding how is the PFAS trapped for the drinking water? I think so. You're just going to answer it. I thought it was. I'm thinking it's membranes or any chemical reaction that would remove or detect PFAS.
That's really good question. It's coming in few slides. Okay.
Yeah. Understand.
Okay. So yeah, we are going to talk about that in a few. So first, the problem, right? So the problem is that we have to solve the problem, right? We have identified the problem, and this is a huge problem. We have to upgrade the water utilities for this. So this is, and the issue is that who is going to pay for it? Not the companies that have caused the contamination, but the public has to pay for it. Good news for my students and whoever works on PFAS industry is that there will be a lot of investment. Okay, so students in environmental engineering and whoever is working on PFAS, there is a lot of job opportunities now for tackling this problem. So that's in other way a good side for students probably. Yeah. And so if you want to, before I go to the drinking water treatment side, if you want to understand how PFAS is prevalent in US, like this is there are different maps for US, for Europe, for Asia, but this one is really nice. You can look at this. I will show. So if you go to this link, like you can just look at it, Environmental Working Group, EWG. If you just write Environmental Working Group, EWG PFAS interactive map, you can go to this map, and what it shows, if you look at it here, this shows the US map with all the PFAS contamination. It's not all the PFAS contamination site, but where most of the monitoring is happening. So you can see different colors for different things, and you can click on each of these dots to actually see the location, the amount of PFAS in each case, and what type of metrics there is. So the light blue is for drinking water above proposed limit, so the regulatory limit. The dark blue is for drinking water below proposed limit, and then you see the purple one is for military sites. So if you look at here, so here in Nebraska, we have, actually we don't have a lot of drinking water like issues in most cases. There are few, but you see compared to that, we have a lot of more military sites because Nebraska was home of the Strategic Air Command during World War I, and we have like major Air Force bases here, military and Air Force bases here. So if you look at this, you can click on them and you can check the concentrations, and you will find that military sites have much higher concentrations. So they will be even in ppb, like 1000 ppb level, compared to 1000 parts per trillion level then compared to just drinking water's concentration. Okay, so this is one place you can look for PFAS in your community. So now coming to the treatment. So how do we solve the problem? So there are two parts of the problem. So one is PFAS is a chemical that you need to take out from water, but the other part of the problem is it's a forever chemical, right? So the carbon-fluorine bond you need to break, carbon-carbon bond you need to break. So there is a part where you want to separate it out from water, separation process versus destruction process. For separation process versus destruction, so at this point, you can consider ideally if we could have biological treatment process. So if you look at this, this is a diagram from a few years back from an industry website, but it kind of gives like really good overview of several technologies. So if you look at here, nanofiltration, ion exchange, reverse osmosis, and granular activated carbon, these are probably the most used technologies, conventional technologies that are being used for PFAS treatment. Reverse osmosis is nanofiltration, reverse osmosis. These are really, really good. They can take out, especially reverse osmosis, they can take out any PFAS because reverse osmosis membranes are very high pressure membranes. They have very narrow pore size, and they can actually take out anything. They are used for desalination. We are talking about salt concentration. So they can take out anything. So you can do it. But the problem with reverse osmosis is they are very, very expensive because you have to push water very high, so they are very energy inefficient and very high cost. So activated carbon is probably the cheapest option, but unexchanged resins also work well. So these are the two most used option for water utilities right now. They are, and depending on the water utility size, water utility, what they have already in the system. So different utilities are trying to look at different parts of it. But all of these processes, they just take out the PFAS, but then you have to replace the media because you are concentrating PFAS in that media, and then you have to destroy it somehow, which these technologies don't, right? But you could look at technologies that can destroy either by catalysis or plasma or electrochemical technology or photocatalysis or even biological treatment process. This could work, but in many cases, electrochemical plasma photocatalysis, they may be a little bit high cost or low efficiency. Especially, it would have been best if we could degrade through biological processes. If we could have microbes, bacteria to do this for us, that would have been the best. And it would be the cheapest, but it's very, very low efficiency. So in this diagram, you can see. Okay. So the point is, there are two parts of the problem. In many cases, we are solving this problem by this, but this is not the perfect solution. Now we have to treat or destroy these PFAS that we are also capturing from water. Okay, so that's where my group is working mostly on advanced materials to design new types of destruction processes, PFAS destruction processes. And the other part is these are very, very expensive. No matter which process you go, they are very, very expensive still. Okay, so this is another way to look at it. So typically, PFAS contaminated source water comes in drinking water utility, and then we want to remove PFAS and treat the water to send to different homes. Right? You can also do some home treatment with a reverse osmosis membrane if you have it at home. Many, like Nebraska houses have reverse osmosis. People use reverse osmosis to take out salt from water, like hard water. We have hard water. Many times people use reverse osmosis. So it's good to have reverse osmosis in house if you can afford it, because it will take care of it, the PFAS also. Okay. One of the thing happens that all these technologies are really good for taking, like not RO, but RO can take out almost anything. But activated carbon or iron, they are more effective for long chain PFAS, but not for short chain PFAS. And again, what I said, like the other part of it is these removal efficiencies, like how efficient these technologies are for taking out PFAS, will depend on what type of water you have. Do you have salt in it? If the pH is changing, all these things, and that will also dictate the cost. So these are kind of like some visuals of how different technologies look like in a plant. So these are the activated carbon are basically charcoal type powder, carbon-based powder, and you have like these large like flow-through systems where you have activated carbon filters through which water is passed, and then you have like PFAS taken or other contaminants also taken off. So this is the ion exchange resin platforms, and this is membranes. So basically membranes are like this, filtration membranes are like coiled like around this, inside these individual pipes, and then water flows through the pipes and go on the other side. So comes through here, goes on the outside, so they go through the filter through the membrane, and that's how you do membrane type of, and you see a lot of different membrane pipes are there. So that's how you scale it up. So there are different ways to do it. So again, the issue is at the end of the day, we have this, however we are doing separation, but we are not really solving the problem of PFAS by not, like, we have to destroy it. So that's one of the targets. So what we are doing, we have been fortunate to have several projects with different, we have been working on PFAS from 2018 now. It's been 8 years. And we have been supported by different agencies. And what we are doing, we are obviously doing adsorption processes, but it's like where We are separating them on different type of adsorbents. We are designing new adsorbents that might be better than granular activated carbon or are similar. Then we are doing all the like different types of we are designing new materials for doing different types of redox processes, chemical processes to destroy the carbon-carbon and carbon-carbon bonds. We are also working on membrane processes with my colleagues, where we are trying to look at how we can combine these reactive processes with separation processes. Okay, I'll go through some of the examples what we are doing, and we can have some questions after that. So I said our group's name is Aich. It has nanotechnology in it. If you don't know what nanotechnology is, the point is we should think about electronics. Okay. So now for some time, for the next 5 minutes, forget about PFAS. Let's go into nanotechnology. Okay. So what is nanotechnology? Basically, if you think about from early age of phones or computers, these first generation computers, each computer was a huge, large room computer, right? They were huge, and now we have smartphone, we have smartwatch, all these things. We have so many electronics. So if you think about the how electronics came about in 1947, it was because of transistor. So this is a picture of the first transistor, which was created in 1947 for semiconductors, and it was this size, right? Now iPhone 16 has 16 billion transistors in it, and this is just one. Okay, so how do we get to very small size of these transistors? Like all we talk about all this chip, we hear chip. Okay, but we don't necessarily know what that chip is. So chip is made of transistors, or transistor make chips. So we are going into very small scale 3 nanometer technologies. Even if you think about the ultra HD TV, QD TVs, like quantum dot TVs that you see in your homes, which are very thin TVs, it is possible because in the background there are very tiny 1 to 5 nanometer size particles that are coated, which light up in different very small energy at very small electrical signals, will light them up at different pixels. So that's why we get those sharp images. Okay, so what I'm trying to say, because we are able to design materials in very atomic scale level, okay, in nanoscale, which is 1 nanometer is 10 to the power 9 meter, we can design materials and change properties within that level. We can design this type of electronics. Okay, all we are trying to do is create different types of materials. Now, how are they different from chemicals? Okay, think about sugar versus sand. Okay, when you put sugar or salt in water, okay, they dissolve and completely miscible, and we don't see their individual structures in there. But when we think about sand, we are putting sand and we can grind it. And if you think about the smallest level of sand, even if you put it in water, they are not necessarily dissolved. They are still in solid particle. As a solid particle, they're dispersed in water. They're not dissolved in water, completely molecularly dissolved. So that's when we can get nanomaterials. And the other part of the point is, like, if you think about the other part is that in that level they can get properties that are not possible in bulk properties. For example, if you think about graphite, right, or pencil lead, graphite, if you think about all this charcoal and everything, it's all graphite, right? Now there are layers of carbon stacked on each other. If you think about graphite, now graphite is technically insulator. Okay, you don't get electric shock by putting a pencil in the electrical thing. It can burn but not electrocute you, right? But if you take out one layer of graphite, just a single layer, you can create graphene sheets. Now what happens, because these layers were connected with each other with electrons, now this electron got free, and that electron can move through the whole plane of this graphene surface. So now it went from insulator to a highly, it doesn't have any band gap. So graphene doesn't have any band gap, which means it's a highly conductive, it's almost like a superconductor. Okay. So, so this is where the main changes come, right? You can take sand. If you think about silicon chip, what is silicon? Silicon is basically sand. Sand is silicon dioxide, right? We are getting silicon chip, which is very, very expensive from silicon. So basically the idea is when we go into nanoscale, we can create new properties and that can make things possible. So this is another example. If you think about bulk gold, gold is used as jewelry because they are inert and they can be, but they don't come into any functional activity. Like you can't do anything with it unless you are using it for jewelry or sometimes you use it for gold tooth replacement. But on the other side, if you go into nanoscale size within 50 nanometers, so these are all dispersions of different sizes or compositions or different types of shells or gold structures. So what you can see, the colors change with either through the length of these nanorods or shell thickness for a nanoshell, gold nanoshell, or nano cages composition of gold. So what it means with different how we change it, their light property is changing, right? Interaction is changing. So you can change their property, physical and chemical properties by changing different sizes, shape, surface structure. Okay, so this is what is unique about nanotechnology and nanomaterials. So what we do is we design new nanomaterials. We look at their properties and can we use them for water treatment, but at the same time we try to understand if the nanomaterials that we are designing are um, are also toxic for humans or not. Okay, so we designed a new nanomaterial. It's not a new nanomaterial, but we use it first time for PFAS, which is we take these graphene sheets and then we put iron nanoparticles on them. Okay, so this was our first project. What we tried to do is look at, because graphene is carbon based, so they can attract PFAS on the surface because of the hydrophobic attraction forces. On the other side, these iron nanoparticles, they can, if you put hydrogen peroxide there, you know, hydrogen peroxide we use for different types of things. Hydrogen peroxide is an oxidant. So what it can do is iron can break this hydrogen peroxide, create this hydroxyl radical, which is very, very reactive, and that can react with PFAS and degrade PFAS. Okay, so we are not only absorbing, so the PFAS is coming to the surface because of the graphene, but then iron creates a catalysis process that can degrade PFAS. So this is known as advanced oxidation process. So we have seen some evidences that it can do. So how we do the experiments, these are lab scale experiments where we take PFAS solutions and put nanoparticles with it. We do some shaking, but we also add hydrogen peroxide in it. Then after some shaking, we take the supernatant out, we take out some water, we test how much PFAS is remaining in the water and how much is going on to nanomaterial. Okay, so this is some of the results. I'm not going to explain everything, but what this example shows is in this bottom figure, what it shows that we were able to break down a eight carbon PFOA or PFOS, which is this, like if you look at this carbon number, so we could break down an 8 carbon chain to 6 carbon or 7 carbon chain. And then the one issue that we found is that the iron then goes and bind the iron that we are using as catalyst. Some of these iron like molecule atoms can go and bind with PFAS too. So we were like partially degrading some of the PFAS, but not completely. So that was one of the, it was good that it degrades some of the PFAS, but most of it was absorbed on the surface. But some of them PFAS was. In the next project, we are trying to do use titanium dioxide, which is a photocatalyst. And titanium dioxide is used in paints. So all the paints that you see, many of them use titanium dioxide because they can take UV light or visible light or sunlight to create electron and holes. And again, reactive oxygen species that can react with different types of contaminants, and they can degrade those contaminants. So we are using that, and this has been mostly successful. I'm not showing the results, I'm just talking about the concepts, how we are doing it. So you can use this PFAS, titanium dioxide, but you can also put them on the graphene surface. Again, we are trying to improve the efficiency of the metal nanoparticle by putting them on graphene, because once you connect the metal nanoparticle with the graphene, you can enhance their reactivity too. So the photocatalysis activity can be more effective and can degrade PFAS, absorb and degrade PFAS more. Okay. So now when we do it, like I have shown you this example that we put like nanoparticles in there, and nanoparticles are like powders. So one of the problems is we cannot put these nanoparticles all in water and try to, because these are powders, then there are issues that these particles will also move in the water and they will create other sorts of problems. So what we are trying to do is now put these nanoparticles that can degrade PFAS and absorb PFAS. We are trying to put them on membrane surfaces that you can create. Like I have shown that the reverse osmosis membrane in large scale systems, you can put these nanoparticles on these membranes to not only separate PFAS from water, so these are filtration membranes, but also destroy them on the surface. So this is another project we are doing. And there, basically, this is a polymeric membrane surface. And if you look at the top layer, so that top layer has just the nanoparticle sheets, like graphene sheets with metal nanoparticles on them. So on the right-hand side, the figure is just about the top layer of this membrane. So you don't have to have the whole thing as nanomaterial membrane because they are expensive. You can have a polymeric substrate in the bottom, but you can have a very small layer of nanoparticles there to create this separation and destruction. The other one we are working on is using these powder-based nanoparticles, but then putting them as a porous structure by 3D printing. This is one of the projects we have to create like point-of-use filter systems. So in our house, if we want to create a filter for the tap water, we can put it on the tap. We are making very, very small filters but at the same time, we create these filters with metal nanoparticles and graphene together so that we don't only separate PFAS, but also can destroy PFAS in the process. This is another project that where we are looking at, we have our PFAS treatment project, but one of the major issue with PFAS is PFAS analysis is very, very expensive. It needs there is no real-time techniques to detect PFAS because they are very small concentration in water systems. So we have collaborators in Clarkson University and New Jersey and Stevens Institute of Technology in New Jersey. They are designing new nanosensors that can detect very, very small quantity of PFAS in water. And we are trying to combine this sensor and treatment platform together. So they are having sensor, we are having catalyst platform to design a combined approach that we can take in a field and do detection and degradation of PFAS at the same time. The other part is you have seen the examples of graphene and titanium and graphene and materials. So these are good materials, but we can probably find better materials to absorb and degrade PFAS. So now we are looking at, because you can have like thousands of different types of different nanomaterial combination that can work as a treatment adsorbent or catalyst. So now we are looking at AI and ML approach. Basically, one of my students, Jenebu, she is working on identifying what type of materials we can use to degrade PFAS by looking at the literature, looking at information about other adsorbents in the literature for others, and looking at also PFAS chemistry, how you can combine these ideas together. One of the other things that we are looking at is not only we have looked at lab scale systems, but when we are talking about large scale systems of PFAS treatment, like we talked about activated carbon, ion exchange resins, then reverse osmosis. I said like depending on what your utility size is, like water treatment facility size is, how much population you have in a city, how much water you need, depending on that and what type of water quality you have, the cost of PFAS treatment may change. The impact of PFAS treatment technologies may change, even for greenhouse gas emission for water treatment systems. So I have a collaborator and my lab mate, previous lab mate, former lab mate, Dr. Stetson Wells. He does sustainability analysis. So we are collaborating on a project where we are trying to understand if we design new PFAS treatment technologies to scale them up for water treatment treatment systems, how will the water treatment utilities decide which treatment system to choose? Okay, so this was one of the first paper that we came out with. We were reviewing other papers. Last year, we came out with this paper in NPG Clean Water, and yesterday, actually, our first assessment of how you select based on water utility size, population size, PFAS profiles, like what type of PFAS there is in your water. How do you decide on what type of treatment technology to choose? This paper got accepted yesterday in Nature Communications. Okay, and the last project I will introduce is briefly is the project with Dr. Khan and their group. Okay, so this is very exciting for us. This is a new area. We have been mostly focusing on water treatment through developing materials, but with this project, we are looking at using phytoremediation or plant species to degrade PFAS. And this came from Dr. Sadiq Khan's group. They were working on this plants for different applications and phytoremediation for different types of pollutants. But now we are working to see if these plants can also remove PFAS and take them up from soil, like contaminated soil, not only from water, but then can we use them for treatment of PFAS in larger scale, where it's not only in a smaller scale. Okay, and with that, I will finish. There is a lot of information, but feel free to ask questions. And if there is not much time, you can also send me questions later through email or if it's not urgent, don't call me on the cell phone, but like email. Okay, but I'm always happy to chat. And I think we have some. I love food, so you will always see food pictures in my in my presentations. Okay, so with that, thank you very much, and I'm happy to answer any questions.
Thank you
Okay.
very much, Dr. Aich, for the excellent presentation. So we're, if anyone has any questions.
Yeah, go ahead.
Yeah, hi, Aich bhai, Moin, I'm from Wet 06 batch anyway, from the Bangladesh anyway. So I'm currently in Canada, and I've worked with many hazardous materials like asbestos and other industries also. So PFAS is a growing concern in Canada. But with asbestos, I saw like when it was discovered that asbestos causes lung cancer, the government started banning it everywhere. Like there's no asbestos products right now, but during the 1980s and 90s, most of the household products were made of asbestos. For PFAS, I mean, like people, the Dark Water movie you mentioned, it released in 2000, 2005 or something. So there's not much regulation, not much, like let's say from the government side, there's R&D department, they know about the PFAS and others, but the common public, like we can still find Teflon saucepans and everything everywhere still being sold. So there's no, my point is like there's no active saying from the government to the industries, like you got to stop producing this, you got to find an alternative or do something else. So, I mean, I mean, do you have any like comments on this?
Let me ask you this question. Before today, did you know about Dark Waters movie?
Yeah, I saw it before.
Okay. How many of in the, I cannot see the hands, but typically when I ask this question, how many people actually know about, forget about watching the Dark Waters movie, I would get only 10% of the people probably know about the Dark Waters movie, forget about watching it. Okay. But if you look at the cast of the Dark Waters movie, there are 3 Oscar winners there. It's a heavy cast, right? Why do you think that people don't know about this movie? And it's not freely available in any streaming services. Why? Because somebody doesn't want want us to know about it, right? That's the point. So governments will try to do some things, but there are other forces in place which are in. And I think the thing is that it's not that nobody is trying to do anything. We had a regulation in 2024 on drinking water. The second regulation was supposed to come for industrial wastewater in the last year, which after the government change in the first week, that got canned, right? So if that came, now the problem is drinking water is responsibility for publics and utilities, right? Industrial wastewater is the problem, right? Where the problem is coming from. So when that got canned, it's a very political scenario. It's not necessarily which government wants. But if you look at Europe, Europe has banned. They have much. They don't have a they don't have a drinking water regulation as low as US. But if you look at their product side, they have banned a lot of products. In US, different states like Minnesota, Colorado, Maine, they are actually having consumer products bans on PFAS. Europe has PFAS using, so you can search rich PFAS, RESCH, rich
Okay.
PFAS. This is their program, right? I think Canada is a little bit late. I know about Canada a little bit, meaning they are, and it depends on like US does something, then and Europe does something, then everyone else start looking at it. So it is kind of like that. So I think it's gonna happen, and Canada is starting to do something about drinking water, as far as I know. Then it will follow one after another. But yeah, things take time, and also it depends on political scenarios and how much you can push against corporations too. Yeah.
Yeah. Thank you. Thank you.
Anything else? Okay. Either it was a successful thing or very successful or really stupid. One of those.
So thank you,
Like my
Nirupam. I really
classes.
wanted to. Yeah, I didn't chime in yet. So I first of all, I really wanted to thank you for your extremely great presentation. It was I learned a lot. I'm not sure about others. So this is fantastic. Uh, I but before I close or before we close, I want to ask one single question to you.
Okay.
What we should do in one line, what we should do to solve the PFAS problem.
I think we.
This is recorded line.
Sorry.
This is a recorded line.
No, that's fine.
Just
Look. I have been talking about PFAS like without
any filter.
I don't care. Yeah, and that's what I will keep doing. But I think just telling others is the first step. Like we do individually for research and other things, how we are doing, that is important. But public awareness is probably the biggest thing that you can individually do. Tell other people and like keep campaigning about it. That's the other thing we can do. We cannot change. And I think, and the reason I will say this, because when it happened, when the administration changed, federal government changed in 2025, and they canned those like industrial wastewater treatment, right, side. And we thought, okay, PFAS is done, like on research side, because we rely on which hot topic goes up, which goes down, right? We thought all of that. But this year, especially in the last few months, what I have been hearing is that federal government's one of major priority is PFAS now, still. And it's driven by all the red states in US, which is very, very surprising. But if you look at most of the red states, they are relying on agriculture. And this whole thing about biosolids to agriculture issue is an economic issue for red states. So as long as public know about it, how it impacts different aspects of their lives and economics and health, I think I think PFAS was in that stage that whatever information like from the previous government, there was a massive campaign about it. So it reached a lot of people. So all the states are doing already their stuff, depending on which state. Meaning, I cannot say about Nebraska. Nebraska is actually not doing much. As long as federal government is pushing, Nebraska will do something. If they're not pushing, there is not much. But I would say like more than 50% of the states are actually doing active work on PFAS. And like Florida came out with a regulation, which I was like really surprised about. Florida came out with regulation. So I think because there is public pressure on the cities and states, it's happening. So the more you tell the public and public is becoming aware, that's how we can move things forward. Because technology development is not an issue. I think what I have seen over the years that it's about when the government prioritizes anything, then money will be invested. If the government doesn't prioritize, and that can only happen through public pressure, probably.
Yeah, in the democratic country, when we are in democracy.
Well, now I'm not going to talk about that part.
Yeah, it's like
you take the risk.
Okay, yeah, that's true. And then basically the another part is okay. So I personally feel like this is a great presentation, and we should have at least one more session on PFAS in our Geo-Lesson. So let's look into that. And Adrika, I think we can set up another time to have like more like detailed presentation on like individual PFAS, what is the consequences and so on, and the other technologies, or maybe the case studies.
I think it doesn't have to be me. I think there are a lot of people who are doing like different aspects of it. I can tell you, you can invite Dr. Saeed Iskandar. He does a lot of work on PFAS in landfill, leachates, like waste for compost. I think those are also very interesting aspects, like not only in water, but also other aspects. He is in North Dakota State University. I can connect you with that, with him. He's more like geo-environment side. So I think that will be also very interesting. I'm just talking about water side. That's what I know. But he might be able to give a broader and details. Like obviously, I can give a talk on like I showed individual like 6 slides on my topics. Yes. But I have presentations for what is very, very focused towards my work, like every single topic I touch. So those are different, that I can do. But yeah, anytime. So this is what I tell everyone now, that you can wake me up in middle of night and tell me to give a talk on PFAS, and I will be able to do that. Not in anything else probably, but on PFAS.
Sure. Yes. Yeah, no, it is really nice. So I think we have like a couple of questions. We have a question here on the chat, so you can take a look and answer that. And then Adhika, you can wrap up.
Okay. I think this is more for you, Dr. Khan, and your group.
For phytoremediation, which plants are being used, and what is the final aim of the research is being conducted? Is the bioaccumulation at different plants part or growth hindrance of the plant? The one we are using it is called vetiver grass. So far we got pretty good success. We can have a presentation just targeting vetiver grass maybe in the future. Our next presentation has already been said, but maybe we can present the use of the vetiver grass for the PFAS mitigation, or like an update of our study. That might be a good one. And then we can also invite Saeed Iskandar, Dr. Saeed Iskandar, and then we can also highlight like what work he is being doing. I think that would be good too. So for us to look up.
Yeah. No, this is good.
Okay, this is awesome.
Thank you for inviting. Yeah. Now I am hungry. I need to eat. It's all about food.
Yeah, it's all about food. Thank you. Okay, Adhika,
thank you so much.
It's yours. Yeah, it's like let Adhika have her closing remarks.
Oh yeah. Sorry.
Thank you so much, Dr. Aich, for the informative and engaging presentation. We sincerely thank everyone who joined the webinar today. So the live participants will be eligible to receive 1 PDH hour depending on the registration question that you answered. So the webinar recordings and assessment links will also be provided in our social medias and platforms and other places. So participants who were not able to join can go through the assessment and get the PDH. So finally, thank you all again for being a part of this Geo-Lesson webinar series, and we hope to see you in our future sessions. And thank you, Dr. Aich, for your time and the presentation.
Yeah, thank you, Audrika, for doing all the hard work of organizing it. Yeah, okay. Take care, everyone. Yeah, bye.
Thank you.